Somewhere beyond the planets, beyond the frozen edge of the sun's influence, beyond the place where most people think the solar system simply fades into nothingness, a machine built in the 1970s is listening to something no human being has ever heard before. It is not a signal. It is not a broadcast. It is not a message meant for anyone. It is a low, faint, steady hum moving through the plasma between the stars at a frequency of approximately 3 kilohertz and a bandwidth of just 40 hertz. So narrow and so monotone that the doctoral student who first identified it in the data thought she was seeing things. Stella Koch-Ocker, a Cornell University astronomy graduate student, was staring at a plot of data returned from Voyager 1's plasma wave instrument when she noticed something barely visible in the noise floor. A thin, persistent line that had been there since 2017 and had never stopped. She described it as very faint and monotone. Her co-author, James Cordes, the George Feldstein Professor of Astronomy at Cornell, said when the plasma oscillations are converted to an audio signal, it sounds like a tone that varies. It is a bit eerie. That tone is the sound of interstellar space itself. Not silence, not emptiness. A continuous electrical murmur produced by plasma, ionized gas so thin that there are roughly 0.1 atoms per cubic centimeter, compared to the billions of atoms in every cubic centimeter of the air you are breathing right now. And that faint hum, detected by a spacecraft running on less power than the light inside your refrigerator, is doing something that no instrument in the history of science has ever done before. It is giving humanity a continuous real-time measurement of the density of the space between stars. Stay with me, because what that measurement is revealing about the universe beyond our solar system is not what anyone expected, and the window for collecting it is closing. To understand why a sound in the plasma matters, you need to understand what the space between stars actually is. Most people picture interstellar space as empty, a void, a vacuum with nothing in it. That picture is wrong. The space between stars is filled with an extremely thin but physically real medium called the interstellar medium. It is made of ionized gas, neutral atoms, dust grains, magnetic fields, and cosmic rays streaming in from distant supernova explosions. It is shaped by the rotation of the galaxy itself, which sets up turbulent waves tens of light years across as space shears against itself. It is stirred by the blast waves of exploded stars, sending ripples billions of kilometers from crest to crest through the diffuse plasma. And it is pressed against from the inside by our own sun, whose solar wind inflates a protective bubble called the heliosphere that pushes back against the interstellar medium and creates a boundary at the edge of our solar system. That boundary, the heliopause, is the outer wall of everything we call home. And that wall is not the calm, gradual transition scientists expected. In August 2012, Voyager 1 crossed it, and crossed is the right word. Not faded through, not drifted across, crossed. Solar wind particles dropped, galactic cosmic rays surged, magnetic field conditions changed sharply. Over roughly 2 days of travel, Voyager 1 passed from the sun's domain into interstellar space as if it had moved through a membrane. Thin, abrupt, and far more defined than any model had predicted, the heliosphere was not a vague atmospheric fade into the galaxy. It was a frontier under pressure. And the interstellar magnetic field on the other side turned out to be stronger than many models had calculated, compressing our cosmic shelter more tightly than science had assumed. But the real surprise came after the crossing. For the first several years in interstellar space, scientists could only measure the density of the plasma around Voyager 1 during specific events. When giant eruptions from the sun, coronal mass ejections, traveled all the way out through the heliosphere and sent shockwaves rippling into the interstellar medium, those shocks would excite the plasma around the spacecraft into brief, loud oscillations that the plasma wave instrument could detect. The frequency of those oscillations told researchers the electron density of the surrounding medium. It was like trying to understand what the weather is like across an entire continent by checking a single thermometer once a year whenever a thunderstorm happened to pass through. Valuable but scattered. Then in 2017, something changed. The plasma wave instrument began picking up a different kind of signal, not the loud temporary bursts triggered by solar shocks. A faint, persistent, narrow-band emission that had no connection to anything the sun was doing. It was there when the sun was active. It was there when the sun was quiet. It did not come and go. It simply persisted, year after year, as Voyager 1 moved deeper into interstellar space. Shami Chatterjee, co-author of the study and Cornell astronomer, described what this meant in terms that captured the shift precisely. Now we know we do not need a fortuitous event related to the sun to measure interstellar plasma. Regardless of what the sun is doing, Voyager is sending back detail. The craft is saying, here's the density I am swimming through right now, and here it is now, and here it is now, and here it is now. Voyager is quite distant and will be doing this continuously. If you are the kind of person who stays for the real science, Drop a like right now because it genuinely helps this kind of content reach more people who want to hear it. Think about what that means. Before this detection, published in the journal Nature Astronomy in May 2021, scientists could only take isolated snapshots of interstellar plasma density when the sun happened to send a shockwave strong enough to excite the surrounding medium into oscillation. After this detection, humanity had something it had never possessed in its entire history: a continuous feed, a running portrait of the physical properties of interstellar space drawn point by point as Voyager 1 moved through it at 38,000 miles per hour. The emission had persisted across roughly 10 astronomical units of travel, more than 900 million miles, with an average sampling distance of 0.03 astronomical units. That is a measurement of unprecedented resolution for a region of space that no instrument had ever directly probed before, and what that running portrait is showing is that interstellar space is not the quiet, uniform, static void that models built from Earth had described. It has structure. It has turbulence. The density of the plasma fluctuates on scales of roughly 1 astronomical unit, tracing compressive turbulence in the interstellar medium, the same kind of turbulence that affects how stars form, how the heliosphere is shaped, and how cosmic rays propagate through the galaxy. Cords compared the persistent emission to gentle rain and the occasional shock-triggered bursts to lightning in a thunderstorm. The hum is the rain, constant, quiet, always present, carrying information about the environment it is falling through. The bursts are the storms, dramatic but temporary. Before this discovery, scientists only had the storms. Now they have the rain. Now here is the part that connects this distant measurement back to you. The density and turbulence of the interstellar medium are not abstract numbers. They directly affect the shape and strength of the heliosphere, the bubble that protects every living thing on Earth from the full intensity of galactic cosmic radiation. If the interstellar medium is denser or more turbulent than models predicted, it presses harder against the heliosphere. A compressed heliosphere provides less shielding. Over geological timescales, as the sun moves through different regions of the galaxy, the properties of the surrounding interstellar medium change, and the protection the heliosphere provides changes with them. Voyager 2's crossing data, published in 5 simultaneous Nature Astronomy papers in 2019, established that the interstellar magnetic pressure on the heliosphere is roughly 10 times greater than pre-crossing models assumed. And a paper published in May 2026 in the Astrophysical Journal, tracking Voyager 1's magnetic field observations through 2024 and 2025, found that the spacecraft still has not entered pristine, undisturbed interstellar space. Even at more than 15.8 billion miles from the Sun, the very local interstellar medium around Voyager 1 is characterized by persistent, albeit weakening, intermittent turbulence that may still be influenced by the solar system it left behind. The heliosphere and the galaxy are not cleanly separated. They interact in a messy, dynamic, ongoing exchange that the models built before these spacecraft arrived had simply not accounted for. The question at the center of all of this has not been answered. The persistent emission has 2 possible physical explanations, and researchers have not yet determined which one is correct. The first possibility is that it comes from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings. This would be a significant discovery, but would fit inside existing physical frameworks. The second possibility is that what Voyager 1 is detecting is something called quasi-thermal noise, a different physical mechanism that carries information about plasma density and temperature in a subtly but importantly different way. One that would require existing models of the interstellar medium to be substantially revised. Distinguishing between these 2 explanations requires either additional data from Voyager 1 itself, which is producing less of it every year as instruments are shut down to conserve power, or a new mission specifically designed to study interstellar space with instruments built for exactly this purpose. No such mission currently exists, no such mission is currently funded, and now the clock. Voyager 1 is dying. Not suddenly and not unpredictably, but steadily. 4 watts of power per year lost to the slow decay of plutonium-238 in its radioisotope thermoelectric generators. At launch in 1977, those generators produced 470 watts. Today, the output is a fraction of that. Of the 10 scientific instruments Voyager 1 carried when it launched, only 2 remain operational: the magnetometer and the plasma wave subsystem, the very instrument detecting this hum. In April 2026, NASA shut down the low-energy charged particle experiment to save power, leaving a half-watt motor running on the instrument in case the Big Bang power reconfiguration procedure, currently being tested on Voyager 2, creates enough headroom to switch it back on. In late 2023 and into 2024, Voyager 1 nearly died outright when a memory chip failure in its flight data system caused 5 months of corrupted transmissions. Engineers at JPL performed what amounted to remote brain surgery through a 44-hour round-trip communication delay, splitting the affected software into smaller sections and relocating them to working memory chips. The spacecraft came back, and when it did, it immediately resumed sending evidence of the same persistent plasma oscillations in interstellar space. The machine that should have died in 1981 had survived what could have been its final silence and came back with more things to tell us. On November 18th of this year, Voyager 1 will reach a distance of exactly 1 light day from Earth. A signal moving at the speed of light will take 24 hours just to reach it. 2 full days for a single exchange of information. No human-made object has ever been that far. And at some point in the early 2030s, the power will drop below the threshold needed to run any remaining instrument, and the last signal will begin its day-long journey home. After that, the only continuous real-time measurement of interstellar plasma density that humanity has ever obtained will stop. The map Voyager started drawing will stop being updated. And the window into the space between stars that we opened in 2012 will close and stay closed for at least a generation because no replacement is funded, designed, or approved. Here's what I want you to take away from this. Right now, a machine running on less power than the light above your kitchen stove is drifting through the space between stars at 38,000 miles per hour, listening to a faint electrical hum that no instrument in human history has ever detected before. That hum is not a message. It is not a signal meant for us. It is the sound of the galaxy itself, the quiet electrical murmur of ionized gas and magnetic fields and ancient turbulence stirred by the rotation of the Milky Way and the blast waves of distant exploded stars, measured from the inside for the first time in history by a spacecraft built before most of the scientists studying its data were born. The interstellar medium is like a quiet or gentle rain, Cordes said, and right now Voyager 1 is the only umbrella we have ever held up inside it. When it folds, the rain will keep falling. We just will not be able to hear it anymore. And bolted to the frame of this dying machine is the golden record, greetings in 55 languages, the sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter. 90 minutes of music chosen from cultures across the entire history of human civilization. Assembled under the direction of Carl Sagan, who was a professor at Cornell, the same university where Stella Koch-Ocker first noticed the faint line in the data that turned out to be the hum of the galaxy. The record will still be traveling when the sun has become a red giant. It will still be traveling after every human city and every piece of stone we ever carved our names into has been erased by geology and time. The most permanent thing our civilization has ever made, carrying the sound of our laughter through a galaxy that hums with its own ancient, quiet music. And for a little while longer, we can still hear both. If this kind of story is what you come here for, subscribe right now and turn on notifications. The Big Bang results are coming. The November 1 Light Day milestone is coming. I am covering every piece of it. Drop a comment with what surprised you most and share this with someone who needs to hear it. Thanks for watching, and I will see you in the next one.